My name is Jason Lucas, and I work for Harris Interactive. We're a market research firm. We also do lots of stuff with polling and pretty much every kind of application of data analysis and statistical analysis you can imagine. And today I'm going to be talking about correlation as it's applied outside of the classroom, and I kind of called it a cautionary tale because I've seen so many abuses of the simplest of statistics, and I think that it's best summed up in a kind of a mock course calendar I've seen once that had statistics 150, how to do chi-square t-tests, and then it had statistics 150.5, how to forget to do t-tests. And, I think that we need to be careful in teaching that we can somehow get students to understand what's going into the statistics they're using. But I'll talk about that a little bit more later. In the business world, I think that the very first speaker said it very well when they said statistics are received by the media and by the public as almost these kind of infallible things that come down from the high heavens, and even when they're preposterous. Because there's a number there, there's some added credibility. And I don't know how that comes about. I guess it's just that people don't like to think about numbers, so they say it must be correct. So in the business community, statistics can be used all over the place. And this is one of the corporate slides. Who are we? We're Harris Interactive, the second fastest growing firm in the US. And we actually purchased the Harris Company in New York, and they do the more public policy stuff, whereas we in Rochester, we do more business-to-business research. So the kinds of problems that I'm faced with every day are, what do people think about a certain kind of mop, or who is buying tires of a certain type. We do a lot of work with consumer satisfaction and consumer loyalty. What makes a person stay at a hotel X or buy a particular brand of gum at Y over and over again, which is something that companies are very interested in knowing about. And I've never been gifted with PowerPoint. What's that?
The N on the keyboard.
Oh, okay. Well, that's what I do basically is I provide day-to-day statistical support to a whole bunch of research analysts who kind of do the numbers crunching, and they use programs such as Minitab and SPSS, and these individuals have a wide range of statistical knowledge, and all of these people are presenting statistical results to the business community. And the other job that I do is kind of develop new products that the firm can market, basically new ways of applying novel statistical techniques to kind of the same old problems the industry's been having for. What we'll discuss, really, we're kind of going to glance over what the Pearson product moment coefficient is, and what assumptions one needs to make in using it, and especially how these are violated. And I think that a presentation of how statistics are often abused in the real world, or in the business world, will be helpful to those that are teaching, because you'll understand where things are going wrong, where there's a disconnect between what students are picking up in the class and what they're applying in the real world. What is it? I'm sure everyone knows it's sort of a measure of linear relationship, and it's a sample statistic where R tends to a population value of rho. And I'd like to talk next about some of the pitfalls of using the correlation coefficient. And the first one is something called restricted range. And one of the things that often comes up in the research that we do is that of a restricted range on one or both of your variables. Lots of times we get surveys that come back where everyone will answer 4 or 5 on a certain variable. I think an example would be sort of like the survey that I'm sure all of you people are going to fill out, with how you liked all the speakers. And of course, since everyone loves all the speakers, they'll all put 5 down. And so there really will be very little variance on that variable. And so when we go to do our correlations and we look at the correlations we see, often what happens is, you get something that looks like this, where you've only got, instead of having your whole range of possible scores, you've only got this. Now, I've had clients and people come to me and say, well, isn't this a problem? And at first glance, you might say yes, but at second glance, you say, well, what is the characteristics of the population that you're sampling from, rather? And if everyone in the population thinks this, then perhaps this is the correct correlation to be looking at. However, if you have reason to believe that the population really looks like plot A, and you're just sampling from a biased subset, then you've got to deal with other sorts of issues. And again, if anyone has any questions at all, please let me know. And the important thing for this is we need to know who's filling out questionnaires for satisfaction. Usually it's only people that are very happy with products that you're using, or people that are very unhappy sometimes that you get people. And I think that one of the things that educators need to be aware of is the importance of data quality. What kind of data, just knowing about where the data came from, because you can apply the most advanced statistical techniques, but if you've got poor data sources, or biased samples or incorrect samples, the statistical inference that you make from them really is going to be compromised. Another pitfall is missing data. This is something that comes up a lot in our industry, and how you deal with missing data. And it also deals with the issue of how you code variables and how variables are coded. In our company, computers files are always sent back with the value of -9 for missing data. That means just the variable is not there. And SPSS is what we usually use. They'll normally just ignore that value and say, however, we had a new analyst that had a major project, and they said, they just ran the correlations and reported them to the client. And they presented a really surprising set of correlations because the variables, the range was 0 to 10 on the variable of interest. And the client looked at the frequencies and said, gee, how come you have all these -9s in here? And, as the last point is, the client's not pleased. And how you deal with these things and looking at your data and looking at your frequencies, I guess, are something that, especially when we do more advanced analyses, people think, well, since I'm doing, some fancy regression or something, it's not important for me to look at my data. But I think it becomes even more important to look just at, scatter plots and frequencies and stuff, and things of that nature. Oftentimes we learn that in Stat 1, and then in Stat 2 and Stat 3, that kind of gets sort of forgotten. I think going back to basics is really just something that's very important, unless, and if you don't do that, you can easily get lost. Pitfall number 3. This is something I'd like to talk about a lot, and I don't know if any of you have seen this. This is kind of a famous diagram. It's called Anscombe's quartet. And it's something that we deal with all of the time in the market research industry, especially shapes like this. People are all too willing to take a dichotomous variable and incorrectly apply, Pearson's correlation to it. So you get distributions that look like this, and people will come to me and say, well, what does this mean? And I say, really that's an incorrect interpretation, an incorrect way to go about your analysis. The other thing that looking at scatter plots will give you is, sort of the evidence of curvilinear relationships. These types of relationships are all too common in the markets because there's usually will come a point where people will pay enough for something, and then if they pay more for it, then they'll be less satisfied with it. And I guess the important thing to know is that simply looking at a correlation coefficient won't tell you anything about the underlying distribution. All of these have the same correlation coefficient, and the distributions are obviously different. And I guess what I would like to take from this is that there's just a need to look at your data, to go back to your data as much as you can. And I don't want to say be data dependent, but always remember what you're doing and where your data is from. And pitfall number 4 is transformations. We've always been taught that linear transformations don't affect correlation. However, one of the things that's often done is to take a variable that's measured on a 1 from 100 scale and say anyone that answered a 90 or above is a 1, and everyone that answered below is a 0. And there's reasons for that, because the human brain doesn't really like to deal with kind of continuous numbers all the time. It's a lot easier to report on a graph to a chairman of the board or some other somewhat important person, a graph where you've got the group of people that answered 90 or above, and the group of people that answered below, versus to report regression lines or something of that sort. And one of the most popular things in the marketing business world is that of the top 2 box. On a scale of 1 to 7, it's almost considered a given in the business community that you say anyone that answers within the top 2 box of your scale is obviously satisfied, and everyone that doesn't is dissatisfied. And the important thing to remember is, and people will come to me and say, why are my correlations looking different, when I've transformed the variables in these ways, is that these kinds of correlations, these kind of transformations will change the types of results that you get. I guess this is sort of the biggest and most general pitfall that comes about in correlation analysis, is how good is good. I think statistics teachers always want an infinite sample with no variables to do the analysis, so that they can have as much statistical power as possible. But there's a continual need in the business world to say, what is my cutoff? What is good versus what is not good? And I think that it's best kind of described as people will have large matrices of correlations. And I had one client that would actually have different colors of markers, and for each different number of asterisks that they had next to the correlation, as far as how significant it was, they would kind of give it a red or a blue or and there's kind of that's kind of looking too low at it's not taking all of it, it's not correctly looking at the data and finding all that you can about it. I think that there needs to be a need of, and I don't know if this is something that statistics teachers as a community can address, but there needs to be a need to tell people that are not technical users of statistics, that are not going to be statisticians, that are just going to be end users of statistical data, for teachers to present data in a way such that non-technical users can understand the data and the analysis that's given to them. Often we see people that, and clients that receive data analysis from us that has kind of complex results, and they will just simply ignore it because they're not familiar with how to interpret it. And I guess one of the conclusions I'd like to talk about is this of causation and correlation. And I think that there needs to be almost a sort of a better discussion within statistics classes about some of the idea of what correlation versus causation is. And I think this is almost more of a philosophy of science issue than a statistics issue, but I think it's something that's appropriate to discuss. What is causation? It has, there's time factors that go into it. X must occur before Y, and there must be no other possible cause for an event, etc. And people are falsely lulled into the sense of thinking all too often that two events that are correlated are therefore causally related. And I think that we need to explain in a better way how to go about showing causal versus just correlation. And I guess that's the short talk that I was going to give, and I'm really kind of open for questions because I'm curious to see if there's any interest as far as how statistics are applied in the non-academic world. But if not, that's all I have to say. Yeah.
This is a simple layman's example of how you use the correlation metrics to make your decisions or how you find the work. How would you do that?
Oh, well, what will happen is we would get, this is a study that I did last week for a major insurance company. They wanted to know which of their, they had a measure of overall satisfaction with their insurance company. And then they had ratings for this insurance company on a number of different attributes, helpful, friendly, courteous, I don't know. And they would look at to see how much these what's the correlation between rating on overall satisfaction and rating on this variable of loyal or something. And then what this company will do is they'll say, all right, loyalty appears to be the variable that's most highly correlated with overall satisfaction with their firm, which is what we want to better. So what we will do is focus our advertising and our media efforts on increasing, this idea of loyalty.
How do you get around this causation versus correlation, association versus causation?
I think that a lot of it is kind of teaching and understanding of what the data itself is, and because simply doing the statistics won't give you the answer of is this causally related. Even if you do a regression, you can do a regression on Y versus Y on X or X on Y, and you need to have kind of a substantive understanding of the way that your data is behaving and the processes that underlie your data. And I think that if one goes blind into the situation where they're just doing data analysis on something they know nothing about, you can run into fall into that trap where you are making causal inferences where they're not warranted. And I guess it's kind of a call for more people for people to be more cautious in making causal inferences than sometimes they tend to be. Is sort of what I'm saying.
Yeah, I think that's a very important point. And in the typical statistics course, I think you make a lot of fun of say shoe size and not correlate with intelligence and so on. You make a lot of fun of the fact that correlation is not the same as causation. If you don't do the other part of it, talk about what really is necessary to establish causation. And I think the best example I have of that is in Salad's video. You watch the segment on the long torturous process that shows smoking causes lung cancer. You get a lot of ideas of what really has to be improved in the students.
Yeah, I mean that's correct.
This has a practical application to us who are evaluated by our students.
On a 1 to 5 basis. You talked about the restricted range. But for the most part, the top two, bottom two boxes are correlated, are tallied, and then the center one is forgotten. That's
Yeah.
one question. But I have another. My question is more technical than that. We might do a bipolar or binomial analysis of the top two and bottom two. Why don't we develop the multinomial distribution and analysis so we can take in the gradations on the 5 boxes, or I should say the 7 boxes?
As far as applications that we do, this is sort of why, and it's sort of something that makes me groan a little bit with technology, because it makes some of these multinomial analyses a little too easy almost.
Is there such an analysis?
Yeah, one of the things we do is we can do something called multinomial logistic regression, which is where we take, and this is something that we do a lot, where you've got 3 choices. It could be, Clinton, Dole, or Perot, one of the, and there are different factors. You can look at that, but the problem with those sorts of analyses is that they have lots of restrictions and assumptions that you have to put on them about the way that the variables behave. And technology, the technology exists out there for people that don't know how to do the analyses, to do them all too easily. I have people that are coming to me that say, how do I interpret these odds ratios that are coming out of this multinomial logistic regression, which is really something that they've never dealt with before, but because the Windows-based program now will have it at the click of 2 buttons, it's a real challenge. But as far as the most correct way of looking at things, yeah, you're right. There is a place for both an ordered, outcome as far as a dependent variable, or a unordered multiple choice sort of situation.
So you're saying there is such a technique out there, but I have not.
Yeah, but there are techniques out there that can do that. And there's.
And you say they're readily available.
Oh yeah, there's always things like the rank order, Spearman's rank order and stuff like that. But I think that when somebody was talking about earlier non-parametrics, people have really kind of forgotten about a lot of these other techniques out there. People know Pearson's R, that's what's known. And that's, in a way, is too bad. Yeah.
This is less a question than a sort of commentary and suggestion. There's a professor of statistics at the University of Liverpool in the UK, who I came across, I forget his name offhand, but if I can, I'll try and dig it up during this meeting, who was very dissatisfied with the naysayers who say that AIDS is not caused by HIV, and started looking at the causation and correlation. And he's developed quite an interesting website where he says after looking at all this, he's now less satisfied with the HIV hypothesis. And he goes into it quite considerably and argues about causation and correlation in a way that I've thought of using in my more advanced courses as a basis for debate on this particular issue. It's quite thoughtful and provoking. And this is not an extreme person. He hasn't started off from an extreme. He's come at it from the other end and been rather dissatisfied with the statement that HIV causes AIDS. He says there are other models that at least are competitive. It might be worth some look at for people who are interested in web-based sources of these research.
Well, I guess to kind of conclude, I'd like to just say that, if I can have a simple message here, it's sort of, one is that there is a need to look constantly to go back to your data, be it scatter plots or just simple distributions of frequencies. Two, that there's a need, I think, early on to distinguish between what causation and what correlation are. And it's much too often kind of forgotten in some of the technicalities of statistics.
And it's basically a conference for math teachers who are teaching introductory statistics at the high school level or at the college level. And we'd really like an example from industry, okay, a case study, Can you come in and do that for us? And he said, what we really want is something very simple, but something that the participants can kind of take as their own and go home and present it as they're the expert. Okay, I can try this. He says, and oh, by the way, I'd really like it to look at how just applying the formula might lead you to the wrong conclusion. And what else is there, out in the real world, aside from just applying the formula? And way back when, I came up with a title that's printed in the handout. What do you need to know about your data? And as I started to think more and more about what I was actually going to say, I came up with, what is it that makes statistics different than mathematics? I mean, they both deal with numbers. There's probability theory, but I'm not going to talk about that today. They both deal with numbers, they have formulas, things like that. But what is it that makes it different? Okay. So I'm going to start off a little bit with a case study. And here's some information. There's 2 groups of data. I have them sorted from largest to smallest, but take a look. They're called Group 2 and Group 4, and you can look at the table of data and say, are these 2 groups different? Somebody comes to you, okay, if you do consulting, and they say, I have this data. Can you tell me if there's a statistical significance between these 2 groups? I say, sure, okay. Well, as any good introductory statistics instructor would do, first thing you have to do is plot the data. Right? That's what we always teach in our classes. So let's take a look at the data. And one way that I plotted it was just a simple histogram. And the data that was under Group 2 is plotted here in black. And the data for Group 4 is in red. And I look at that and I say, gee, they look different. It's reasonable. Well, part of what I do in statistics, I'm also interested in the time order of things. Now, I just use, Minitab to plot this out. And so Group 2 here is in black. It's a little hard to tell the difference between black and red up on the screen. This is Group 2, the first reading, the second reading. And then up there is Group 4, the first reading and the second reading. They happen to be made actually on the same day. But just taking a look in time order, didn't appear to be anything unusual in time order. So look at the plot, you say, yeah, I think there's a difference. And actually, if you do a student's t-test, 2-sample t-test, you find there is indeed a statistical significance. I mean, the t-value is over 15. It should be, it's kind of obvious. And, if you want to, you can work through, that equation, the formula. I use Minitab, but the t-value is over 15. I mean, there's greater than a 99.9% chance that they're different. Okay. So I applied the formula. I find out they're statistically significant. Okay, in my mind, this is the mathematical side of it. I used the right formula. I checked all the proper assumptions, all that good stuff. Okay. They're statistically significant. But what do I do with that answer? And to me, it comes more to what I'll call the statistical side of it. Okay. What conclusion should I draw from the fact that they're statistically different? Well, it all depends on how the data was collected. Okay. And, what question is being answered? And unfortunately, the question that's being answered is defined by how the data was collected, and it's not always the question that's being asked. Okay. People come and say, gee, I have this data. Can you tell me what it means? So let's take a look at the actual facts of this case study. Those 2 groups of data are repeat measurements of the same sample. It was not a destructive test, so we could take the same sample. And it's almost like a piece of saran wrap, clear film that you would, cover something with. And we were measuring the optical density of a clear film. So you're trying to see what kind of color is in there. Even though it's clear, it has some color to it. And we wanted to know, when we actually set up the gathering of the data, we wanted to know if there were differences in instruments. And so we took the same sample, and those 15 measurements that you saw, well, they were actually collected 3 a day on 5 different days. And those 5 days, they covered about a 3-week period of time. The reason we did it that way is we wanted to get an idea of how repeatable were the instruments within the same day. Was there, how repeatable were they over about a 2-week period of time? And then how do they compare to each other? Now, that would be above, I would expect, above the level of introductory statistics where you may be hoping to go. But in fact, the two groups are really, that statistical significant difference that you see is really a difference in the instruments. Okay. Well, that's easy to see because we, methodically went through and said, now where did this data come from and, how is it laid out? Well, the real problem, though, or what I'll call the essence of the problem, is what happens if you had different samples measured on different instruments. For example, you have one manufacturing operation in Oklahoma, you have another one in Illinois. They both make the same product. They send information back to you, and you can very easily get those two columns of 15 numbers. They were made in different places, and they were measured where they were made. Could you say whether the difference that you see are due to the sample or the instrument? I've included some data here. And the case study data, the data set that I've provided actually has about 600 observations in it. It was a very extensive study that we did. I'll talk about the structure of that data set. I'm picking and choosing to show you the kinds of things you could use it for in your class. But I was hoping to give enough information that you could liven it up in a few different ways at different times. But here I have two different samples. I have sample A up there and sample D over here. So they are functionally two different pieces of film. And as luck would have it, one was measured on one instrument and one was measured on another instrument. There is no way to tell whether the difference that you see there, and if I ran this through a t-test, it's significantly different as well. There's no way to tell whether that significant difference is due to sample or if it's due to the instruments. So what makes statistics different is that you need to think about how was your data collected? What really is in that data? What information is really there? I put it in terms of, before you can draw any conclusions based on the statistical significance, you've got to ask questions like who, what, where, when, why, how. Not only was the data gathered, why were these samples used or whatever, but you also have to ask about the measurements. And a lot of times people, take for granted that the measurement system is right. It's like a computer. If it gives you a number, it must be right. Ever have that? But think about, one of the most popular measurement systems most people are very familiar with is your basic scale. And the repeatability of your bathroom scale is one thing, and when you go to the doctor's, it's repeatable, but generally at a different mean value. Did you ever notice that? Sure have. So if I wanted to have fun, I could have brought in a few different scales and got some volunteers, and we could show measurement variability. Okay? If you really wanted to do something that was interactive, okay? But it's true. And then of course there's variability in everything, and we always, when it's your bathroom scale, you always believe the lowest value, but that's another story too. Not the mean, the lower. So, are there any questions so far from what I've talked about? Yes?
With your optical density, you circulate standards, like pieces of material that are measured very carefully, and then you send those out to be measured in between in an unknown way?
You should do that. Each instrument would have its own standards, okay? And if they have a time component to them, that's a problem. If they need to change. We were just looking into a problem. We're talking a bit about how we came to gather this data, and those are the things that you do to improve your testing ability. But how should I say this? With so many different places that manufacture, with the global market or whatever you look at, we try to, all companies, all the companies that I work for make all different products in different countries, let alone different factors within the United States. It becomes very hard to run those round-robin studies. If I really wanted to tell if two materials were different from, say, made in Oklahoma and made in Illinois, I would collect the samples and measure them at the same time on the same instrument. That's how you get rid of the instrument problem. But if you just get data, somebody comes up and says, oh, here, I have these two groups of data, are they different? Okay, you can do the math and say, oh yes, there's a statistical significance, there's a significant difference there. But when you start asking, where did this data come from? Oh, it's, this, group A was made in or made in Oklahoma, and group B was made in Illinois. Oh, interesting. Where were they measured? Oh, they were measured, these are the QC data that came right out of the lab. Oh, okay. What the statistical significance means depends on the answers to those questions. If you don't keep asking, well, if you stop at where did the samples come from, the difference must be those samples. Unfortunately, just if you want to think of it, the difference between mathematics and statistics is you have to be awfully suspicious as a statistician. Yes?
There are of course, other possible sources of difference
Yes.
between the two samples. The operator who does the measuring, perhaps. Right.
A variety, yeah. Well, those are the kinds of questions that you need to ask. And the data set that I provided, I've gone through in the handouts and on the slides, it goes through who, what, where, when, why, and how. What I'd like to do is talk a little bit about the case study, how we came to have the 600 data points, why we ever did it in the first place, to give you a feeling for what it is you're looking at. And then I just put the who, what, where, when, why there in case you need to refresh your memory when you get back to your own class.
There's actually a huge field of applied probability, applied mathematics, where people do this kind of thing also. So I don't really see this between math and statistics. There's theoretical statistics, but nobody ever has the data.
Right.
Applied statistics, they do. And theoretical mathematics, they don't worry about applied mathematics.
Possibly I picked the wrong title as far as the difference between mathematics and statistics, and that's very possible. But what I was trying to go for is, why just applying a formula?
Sure.
The textbook kind of thing, at the end of the chapter, there's problems.
Same is true with applied
Right.
mathematics.
Right. So let's talk a little bit about where it all started. It started because we had some product that when it was made, manufactured and shipped and tested for density, there were no obvious problems. It was within specifications and control, all that good stuff. Goes on to another customer, internal customer for another operation, and all of a sudden, what did you do? This stuff is, we have terrible problems. There's been a shift. It's dreadful. Okay, so you start looking into it, and being applied statisticians and suspicious, the first thing you do is call back some of the sample and say, okay, let's see what's going on. What is it that you are looking at? When you bring it back to the original instrument, it still looks good there, and so it was obvious that there appeared to be differences between the instruments. So we wanted to set out and have a study that looked at all of the instruments that could have been involved in this particular operation. And so who started this? Well, there were the engineers who were trying to understand the differences in the measurement. They wanted to know if differences exist. We took what I call stock samples. We chose 4 separate samples, and in the data set they're labeled A, B, C, and D. And they were specifically chosen to span what we'll call the normal range of production variability. So you didn't have everything at one a high point or a low point. We wanted to know how repeatable the instruments were within the normal range of variability. And so those 4 samples were specifically selected And so it wouldn't be outrageous to find, statistically significant differences between them because they were handpicked in that fashion. Now, each one of the samples, you can imagine we had 4 samples. On each one, we took a small picture from different places. So we took 3 random samples, okay? And that's called location in the Excel file that's been provided on the data disk. And that's trying to take a look at what kind of variability do you expect just across, this sheet of clear material versus what you might expect from piece to piece. And then, since it's a non-destructive test, but it would be terribly affected by fingerprints, we mounted them in your basic slide cover. And by slide, I mean a picture slide, so that you could handle them by the cardboard around them. And every time they were put down, you were able to look in the exact same place because of the way they fit into the fixture. So the instrument was reading exactly the same place on the sample each time. Now let's talk about the measurements. Who made the measurements? Well, and they're called densitometers, and in the data set you have densitometers 1 through 4. One person did all the measurements on densitometers 1, 2, and 4. He did all those measurements. And all 3 of those are actually located in one area. So one could be a backup if there was some kind of problem during manufacturing. One might be considered a backup to another. So we were interested in, 2 were in the same lab, 1 was in the same building. And so kind of interested, if they had a backup and they went to the other room, what kind of differences might we see. And then the densitometer called number 3 was actually located at a totally different place. And all of those tests were done by another person, the person who generally uses that instrument. And so all the tests were done by standard procedure, and within the densitometers, 1, 2, and 4 were all done by one person, and number 3 was done by a different person. It's a fairly straightforward test. You drop the slide, you hold something down, you read digital output. So there's not a lot of, the slides are already prepared, so there's not a lot of test variability that you might come up with procedurally in this particular test. Again, we were interested in the stability of the instruments as well. Are they drifting with time? And so we had the samples read 3 times in a day to get short-term variability. And then we had that repeated maybe every 4 days, so that there were 5 different days we did it, but they weren't, Monday through Friday of 1 week. It was taken over took about a 3-week time period to do that. And, when samples A, B, C, and D, and then of course there are 3 repeats, so there was a total of 12 actual slides that were gone through. When they were read, they were read randomly each time, so they weren't always, taking one off the top and put that in. So we tried to take care of that kind of variability. Because the question we really wanted to answer with this data, and it extended to 4 densitometers, not just 2. And of course, I picked out some data because if you want to use it in a class of introductory statistics, 600 data points can be a little overwhelming. Okay? But I included all of the data on the disk because as you go through and look at the data, some of the instruments have significant differences in variability. And so if you're teaching about an F-test and how do you tell, or make up a problem that says the variability of this instrument is generally thought to be this, and we've just taken these samples, so I tried to give enough data, hopefully giving you the opportunity to use it in a lot of different ways if you wanted to in your classes. I talked about the data set having 4 samples, and there are 3 locations for each 4 instruments. I've only talked about the blue density, but there are columns for visual density, red, green, and blue. Okay. If you think about it, you have a clear wrap that you're going to put, say, over meat at Wegmans or at the grocery store. You wouldn't want that to have very much of a green tint to it. You could just imagine how much you would sell if it had, just a slight green tint. Really wouldn't show up too well until you put it over red meat or chicken. So that's why things like this. Why would you ever be interested in the color of clear material? It has enough of a tint to it. You don't want to use it in certain applications. There's a column labeled day. As I said, we did it over 5 days. Okay? And then a column labeled test. So within day 1, it's test 1, 2, 3. Within day 2, test 1, 2, 3. And again, I hope you can use the data in many ways to illustrate the concepts, because depending on how you pick and choose the data, okay, the first data that I took, I had the same sample measured on 2 densitometers. And so I can say, is there a difference between the densitometers? But in the second sample that I took sample measured on this densitometer, a sample measured on a different sample. Now you can't really tell the difference. Okay? If I really wanted to tell a difference between samples A and D, I should pick out data measured on the same densitometer. Okay? So all of those options are available for you to take a look at in the data set. Questions? You're all going to sleep. It was a good lunch. Now, I'm not above. When I teach at night, most of my students are working adults, and they work for 8 hours, and then they come and listen to me lecture for 3 hours. And I'm not above making them stand up and do follow the leader or something. Well, they're sitting there, and I can talk for a long time. I don't have any problem talking, but it doesn't do them a lot of good to sleep through it. So, do you have any questions before I go on? You're all experts, right? You can stand up and use this case study. My biggest fear was that it was too elementary for what you were looking for. But in my discussions with Bob Johnson, he kept saying, this is introductory statistics, keep it simple. So hopefully it's simple enough, and you would be able to make up problems based on the data. John?
I just want to add a comment. The most important part of the process of analyzing someone else's data is to go through this interview process with them. They'll come to you with the data, and you start to ask lots of open-ended questions like Dave suggested, and they'll come up with a tangled verbal account of how all this information was gathered. And what I do at that point is sort of draw a schematic diagram of where things are coming from, sort of physical layout, if there's a physical element to it. But ultimately, if I can then take that schematic and convert it into a structured diagram, which is an entirely different topic, but that structured diagram, which is what I've been kind of taking notes on here and writing out that she's talking about, can be converted to an analysis of variance table, proper analysis done on that. So taking it from this tangled verbal account and this interview process is really important. It really tells you how you can analyze the data and inferences are available.
Yes?
Was any data measured on the line voltage for the indigenous? Because my experience just traveling around the world is that there seems to be an awful lot of effects. If you go to Queensland, Australia, where the voltage is 250 rather than 220, different things happen.
No, I do not know that we see anything to check in that fashion.
Because that would explain this drift.
Right, that could explain why it's there. Right, and once we discovered that significant differences exist between the instruments, then it's time to get people who understand the instruments to understand that and write out the standards, use the same standards on each one. Okay? This case study really went toward, are there differences in instruments, or is there something happening to the product from the time we make it to the next user operation does something with it? So, yeah, the results of this, aside from saying, yes, they're different, and, it's not because of the instruments, is then to have a whole effort to understand and standardize the instrumentation. Yes?
He was just telling me that this data is on this logistic we were given in the beginning.
Yes, that's my understanding. It's an Excel file.
Okay.
I just wanted, I don't have a descriptor page in the Excel file. So when you open it up, the first column is sample, the next column is location, the next column each day, test, and then visual rendering and look. So I wanted to spend a little bit of time to explain to you what it is you're looking at. Yes.
How often do people call you in the design stage rather than waiting until they collect the data?
Well, I generally work in a major client area, and so for those people, I'm there from the design stage. Okay, I'm involved with things that are going on. But oftentimes you get someone who comes in and says, here, I have this data, can you tell me what it means? And unfortunately, when you ask the questions and you get this, tangled web, you can't get there from here. You get the data that was measured here on one instrument, and so unless you want to make, a sweeping assumption that the instrument's limits in effect, and then talk about the vacuum scale, just to put people back into reality. Unless you want to make that sweeping assumption, you can't tell. You really can't tell from the data. Yes, there's a difference, but structured in this way, I can't tell you exactly where it's coming from. And if you work with people long enough, you can get bites them once, and the next time they come and say, I want to do this. How do I want to collect the data? And that's, what I'm trying to get at with the talk. Not only, here I have data collected in a bunch of ways. And the reason that we did the study, that the case study data is structured so that you can determine differences between these four samples and differences between the instruments, not only with respect to mean, but variability and all that kind of stuff. But the idea is you have to know where did this data come from. Because if you think about, most of your statistics text, introductory statistics text, I have this data, one of the ones I can remember, high temperatures in Seattle versus high temperatures somewhere else. Makes sense, and people can run through the appropriate formula to say whether there's a statistical difference in the temperature of these two locations. For thermometers, you don't think they're too far off until you get one and put it close to where you had one. And then you realize they're about as good as vacuum scale. But you would hope that the National Weather Service has this, repeatability from place to place. It's the kind of question, though, you need to ask about data. And so as a final thought, are there any more questions about the case study data?
Comment and appeal.
A comment and appeal to me?
To you and actually to the whole gang. One of the things that I'm involved with, and I think David showed some of the sessions, the Journal of Statistics Education Data Archive. And so we've seen that we have data sets like this with a file with it that explains the variables, and then a short paper that talks about how you can use this in class. And we always need good submissions to this, so I'll bug Patty afterwards to see if she will write something up for that. But I think a lot of you have heard good ideas of good data sets, and so feel free if you're interested in writing one of those data set articles to contact me to see if we can. So it's a good resource, but it depends on people sharing it with that.
Well, I have it in here. I call it the last thought. Are any of you familiar with the book? It's titled Statistics for Experimenters by Boxhunter and Hunter.
That's a classic.
Oh yeah. It's a great book. And in there, they describe an experiment, and it's it's in the section on paired t-tests, but it's a real eye-opener to think about how do you collect data. And so, whoops, here I thought I went all the way up to that. It discusses the evaluation of sole material on children's shoes. Okay? And so I want to look at, I have two different materials I could use on the soles of children's shoes. And any of you who have children know that, some of them grow out of them and some of them wear out of them. And you want something that's really, going to hold up to kids. So how could you use 10 children to compare two shoe materials? Well, one option would be to take 5 of the children and give them a pair of shoes made with material A. And take the other 5 and give them a pair of shoes made with material B. And then after some period of time, 2 months, collect up the shoes, measure the tread wear, and see how did material A fare against material B. That makes sense. Another option, though, would be to have each child wear a pair of shoes where one shoe was made out of material A and one shoe was made out of material B. And also to randomly assign which feet get which material. And why would I care about that? Think about hopscotch. If you have a child who loves hopscotch, or I have one who slides into every base, but it's always with his right foot. Okay? And then after this 2-month period of time, you compare the tread wear differences within each pair of shoes. Okay? So there's 2 different ways I can use the same 10 kids, okay, the same amount of sole material to evaluate which material is better for making children's shoes. Does one of them seem like it would be the more obvious choice? Okay. They both sounded reasonable, right? When I started going through this, unless you've read it before, they both sound reasonable. The first option, though, includes the differences in the activity level of the children. If I have 5 children over here and I give them shoes made out of material A, and I have 5 over here and I give them shoes, even if I randomly assign the children, I may have kids over here in that 2-month period who particularly like computer games versus ones over here who like to skateboard. Not all of them, but a few of each kind. And so what you end up doing is confounding the activity level of the children with the differences in the shoe material. Whereas in the second option, each pair of shoes has a material A and a material B. They see the same puddles. So you take out more of the activity level. You still don't take out the foot-to-foot differences, okay? But those 2 feet go the same place. So option 2, I'm ahead of myself, but I don't know how to go back. So but option 2 is, I'm honest,
P goes back.
What's that?
M goes forward, P goes back.
Oh, wow, thank you. This is the first time I've given a talk with using PowerPoint, so I'm pleased that it's going this well. So option 2, actually, if you really are interested in the difference in the sole materials, is a better way to go because you're not, it's not depending on the activity level of the children. And I think that makes the point as, that I'm trying to make here as when I said, what do you need to know about your data? How was it collected? It's this tangled verbal account of where did it come from that helps you know what, if there's a difference or there's not a difference, what is it in? Is it a difference in sole material or is it a difference in sole material and activity level of the children? So you need to think about how the data was collected to know what answer it's giving. And basically, the formulas used in statistics are valid. They yield evaluation of significance, so you can decide whether it's statistically significant or not. But the conclusions you draw totally depend on how you collected the data. That it's significant or not significant. Mathematically, everyone with the same set of data comes to the same conclusion with respect to significant, not significant. Then you really have to go through and ask, what difference is it that I'm looking at? Yes?
Well, actually, this last one is a power issue rather than the kind of variables we were talking about before. Because here you have the same variables, and it's just as good, except that if you do the pairs of on each individual, you take out the individual differences, variations, whereas the first one you didn't.
Right.
But if you got significance in the first one, it would mean the same thing in
Right.
either case.
Right. But they could be run either way, but it's a pair, like I said, it comes up as a paired t-test
Right.
and, you know, increasing.
No, well, it increases the power.
Right. But you could, you know, on a bad hair day, you could assign shoe materials and get a significant difference that was more activity than material.
Yeah, but
I
if
mean-
you assign them randomly,
If
that
you-
would be in the random error that
Right.
we're measuring.
Right. But on a bad hair day, it could get such a sign such that, you know, I call, you know, randomly you try to get rid of everything, but, you know, 1, 2, 3, 4, 5 is one of the random assortments of those numbers.
Correct. That's
So-
involved in those probabilities.
Right, right. So, other questions? I hope this data is something that you'll find useful, the kind of thing you were looking for to take back to your classes.
Are there any other questions? No. Well, thank you very much, Kay. This is